Okay, so this last talk today will take you from optimization, like what Peter suggested, or Peter's talk, to application. So we'll talk today about learning from human experts and machine learning for perceptual user interfaces. So I hope you can hear me well, and otherwise just let me know so I can get a headset. So what do we have in the recent years? So we have kind of a progress in the fields of machine learning and deep learning. And along with this progress, a lot of new novel interaction media technology have come up, such as speech-based interaction. We'll use a lot of tablets or smart watches for interaction. We have full body interaction with the Kinect. We have at least some working BCI interface, and we have a lot of augmented reality and data classes coming to market. So all of that is kind of coming integrated into some idea of the augmented human, so human augmentation, in the sense that the human has kind of augmented senses, which means our senses are integrated, or we have a lot of sensing technologies augmenting our senses, and at the same time we might have current or very novel actuation technology basically augmenting our actions. So along this line, or in this concept, gaze or visual behavior has been handled as one of the promising modalities for future HCI, and has been considered as one of the enabling technologies for VR and AR interfaces. Just to get you a bit of on why this is the case is, and for those of you in the audience who are not familiar with the concept of the visual scan path and visual search behavior, let's do a very nice task. So if I would ask you to find the cat in this image, I guess like after some search, you'd probably see that the cat is at this left corner of the image. And indeed, it took the person, we tracked here 19 fixations, so steady eye movements, to get to the location of the cat in the image. And as you can see here, this search that a person does in space and time can reveal a lot about our actions, intentions, and activities we are involved in. So that's why we use, and throughout this talk, we will talk about the concept of the visual scan path. That means the visual scan path that we do, or the scan path that we take while we're looking at something or searching for something. So scan path research has a very long history, and noteworthy in this realm is, for example, the pioneer work conducted by Yarbus in 1965, where Yarbus asked the study participants to look at the image under different conditions. So some of the participants were asked to estimate the financial status of this family, here shown in the image. And we see here we have different scan paths for estimating the wealth of a person that ages. So while people look at ages, they basically look more at the faces of people. So in the 1970s, Norton and Starr came up with a scan path as a definition, as for a fixed scan path as a characteristic of a given subject given viewing a given pattern. And since then, we've had a lot of research and studies looking at ways to analyze those complex patterns, the visual scan paths in space and time, towards the identification of something, maybe a general visual search behavior. The question that we ask in our research is, how can we enhance user model through scan path analysis? So in the areas that we're working, we use this enhanced user models or cognitive user models to improve usability of our websites or user interfaces, to guide users and make more efficient visual search behavior for assistive technologies in tutoring systems or expertise development. And this is something that I will be talking today and in this last talk of the conference. How comes that we actually work on expertise development? A few years back, I read a very interesting article about one of the chess masters Jose Raul Capablanca, and I found it quite interesting that he learned to play chess at the age of 4 by watching his father play with friends, right? So, and he pointed out an illegal move by his father and then beat his father. So for those of you who play chess, you might know that chess is a very quiet game where nobody will talk about strategies or actions that are going to proceed. So apparently this small child was able to learn strategies and basically gain a lot of domain knowledge only by watching people how they do this. So the question that we've been asking during the last 3 years in our research is, can we learn from viewing experts? So can we build domain knowledge, and can we learn to do image-related tasks better than experts or like experts do? So expertise manifestation in the visual scan path has been one question that has driven us. And today I will talk a bit about the PhD work conducted by my student Nora Kasna in collaboration with the Leibniz Institute for Business Media and the university clinics. So what you see here in this image are so-called OPT images, so whole radiographic or panoramic radiograph images of our mouth, like they are taken when you go to the dentist, for example, which are considered to be probably among the most challenging radiograph images of the body. Why? Because there's a lot of anatomical structure hidden in those images, and a lot of things that are pretty hard to detect going beyond the sole teeth area. So what is interesting here is that there is a lot of anatomical structure that can be basically detected, or a lot of anomalies that can be detected only after a long years of expertise. So there is recently some work being done in the area of automated detection of those anomalies, which is pretty hard for just decision-based or decision support system to conduct, because you need a lot of data to train your algorithms, and not much data is available for some part of the anomalies. So still, these medical students have to go really mass practice. So they have to see a lot of images and to get courses, proper training on how to view and interpret those images. And as you can imagine, similar tasks might be important for any kind of image inspection, given industrial production or any other radiographic images or whatever it might be. So what we get from here is that these students undergo really mass practice during their study to learn to interpret those images. Let's look a bit at this one OPT images that I have here, and I'll show you 2 scan paths. The bluish one is the scan path of an expert, while the orange one is the scan path of a novice, like, for example, me or a medical student in the 6th semester, who probably will focus more towards the sealant areas in the mouth, which is some areas filled in the teeth, or probably very obvious anomalies. While experts, they have very high image coverage. They look for anomalies throughout those images. So the question that we ask is, can we have something, so given the differences are that large, can we have something like an attention-aware intelligent tutoring system, which means a tutoring system that help us to do the image inspection as an expert does it. And of course, there's a lot of things to solve along this path, because as you may know, domain knowledge is not something that is done in a binary fashion, but is something that is increasing over time. And we have here students at different semesters. So from their introductory level, so introductory level means students who have finished their basic medical studies and are undergoing like more professional advanced study courses, domain-specific study courses. So in the 6th semester throughout the 9th semester and the 10th semester, this is where they accept their studies. And this is probably also the level of expertise that you often also see in residents, right? So there's a lot along this development that is gained with regard to the domain knowledge. And as you see here, also image coverage properties will arise. So one problem that we had while analyzing those images is that if we look at the first order statistics, just like having some quantitative measurements, fixation saccades, typical viewing properties, that you won't find any significant differences between those groups. So obviously, despite the long research that has been done in scan path analysis, starting just from manual labeling or AOI extraction or method scrubbing from the bioinformatics for sequence alignments, or hidden Markov model Bayesian statistics. Now, with the development that we have in deep and machine learning, we're basically able to look at these sequences in a more sophisticated way. So what we've done here is that we tried for the basically for the first time to employ image characteristics or image related features along with the eye movement features towards a more advanced scan path comparison method, which we're going to be deep scan. And of course, I will talk a bit about the architecture for each of these steps. You can of course take other architecture components to replace them, but we tried to come up with something here that generalizes well and might be also useful for other tests despite that. So what we did here is that we take so-called gaze embedding. So we take fixation patches around each fixation location, so image patches that obviously correspond to certain stimulus region, and we encode basically each fixation location by a vector that describes the local image properties. We generate such encodings using a VGG architecture, and of course you can also take any other component here to do that. I mean, you could even take something, a network that has been trained to interpret those images to do that. We thought like VGG 16 architecture is pretty easy to compute and can be basically nicely replaced by any other stuff. So what we do then, we have this feature description. So we have these feature vectors for each of the fixation patches, and we use that to create a scan path matrix. So as opposed to a string of characters, which was previously used for scan path comparison. And at the end, we kind of have a reduced problem in the sense that we only need to compare those matrices instead of having those complicated images which needs to be compared. So given, for example, we have two scan paths here, and we have this scan path matrices. So what we do here is that we want to compare them regarding their similarity. In this specific application, we use for the comparison, we perform a local alignment using a variant of the Smith-Waterman algorithm, which of course is also replaceable by any other algorithm that might be more suitable for your task. So it works quite well for this kind of image inspection task. And what we have as a match score, we use the sum of the absolute differences in the feature descriptions of the two different matrices, which is easy to implement and most importantly cheap to compute, right? Because we want to save resources here. And of course, if you ask like other matrices, other metrics, of course, you could use a cosine or Euclidean distance to do that. So at the end, we will come up with a dissimilarity score between the image patches. And of course, the more dissimilar the image patches, the larger the scoring value. Okay, so what we have there is that we can cluster this similarity score of all participants. We clustered them, we used a grammarical hierarchical clustering to do that. Very simple computational framework. And what we found out, and this is basically what is very impressive, is that these findings confirm what we visually observed, that we have experts, they have very high similarity between each other, so they have very similar patterns, they are very similar strategies, how they explore those images. And students on the other side, they have very they have higher variance between with their respect to their scan path properties. We went a step further and we said, given that we have now those scan path models of the experts, what can we do? We combined different techniques here to guide attention. So we coined it like a subtle gaze guidance, what we did here, in the sense that the aim is to not include any important semantic information on the image. Rather, we do it gaze dependent. So we will look at where is a person looking at, what is his or her visual search behavior, and then we guide the gaze. So we present a stimulus, and the moment that the person will basically go with his or her attention toward the stimuli region, this highlighting will remove. So during the pandemic, we basically didn't have much choice of trying it in the large scale, but we managed to successfully guide the gaze of naive subjects, we mean computer science subjects, through OPT images. I think we had more than 20 subjects with whom we tried out this way of subtle gaze guidance, and they all reported that they found the tool to be highly usable, meaning that it has also great potential for students of trainees. And we are thinking of ways of implementing this kind of tutoring systems for the medical studies as well.
Enkelejda?
Yep.
Your sound quality is a little bit variable. Could you possibly
okay. Yeah, maybe the I'm using the EduRoam. Yeah.
Okay, I think if you move closer, it's much
yeah.
less.
Okay.
It's much
So
better.
I'll just try to move closer. So thank you. Yeah. Okay. I'm sorry. I hope you still got most of the parts. All right. So I think this is something that we are definitely going to explore further. So how to efficiently guide the gaze and those tutoring systems, and how to use expert models to train people in a more efficient, but above all, personalized way. So to find out what is the level of expertise of a person, and then guide the gaze or train them according to their image inspection experience. Another application area where we're using that is sport research. So we are working closely with the sport research department, looking at perceptual skills of athletes. So in soccer playing, we had like some recent publications with these collaborations. But I think that a lot of unused potential for all of these techniques, and above all in the intersection of machine and deep learning and human-computer interaction, lies in the medical studies. Now it would be really great to talk to the one or the other here working in these domains and see how we can incorporate these methods in medical practice. Apart from that, in the same application area, like medical application areas, we're working to improve gaze-based control of neurosurgical microscopes. We do a lot of work to characterize or for intelligent sensing of humans while doing different tasks. And of course, one of the most important points while working with such biometric modalities is, I might coin that, is keeping the privacy of these people. So that's why we do a lot of work there as well to develop methods that help us to preserve the privacy of individuals or models that we have in those applications. All right, thank you for your attention. I'm sorry about the sound quality. I hope you still got the parts of the talk. I'm happy to take your questions here.